Hi, welcome to Chemical Bonding. My name is Dr. English. Today we're going to be talking about the basics of covalent bonding. Specifically, we're going to look at an introduction to covalent bonding, the definition of a molecule and a diatomic molecule, coordinate covalent bonding, and finally, multiple covalent bonds. So what is a covalent bond? A covalent bond occurs between two or more non-metal atoms. Non-metal atoms have high electronegativity values. In other words, they're able to draw electrons to themselves and need to gain electrons to achieve a full octet. Since non-metal atoms need to gain electrons to achieve stability, neither is able to completely take the electrons from the other. As a result, the atoms share electrons. They are sharing electrons together, not just taking one from the other, but sharing electrons to achieve stability. If you look at the word covalent, we see the prefix co, which means joint, and valent, which refers to our valence electrons. Hence, covalent means shared electrons. Electron sharing occurs in pairs of electrons. In other words, one bond is going to always equal two electrons. Two atoms may normally share one, two, or three pairs of electrons. The atoms bond because the shared pair of electron results in a more stable molecule. Let's look at an example of this. Say I have a chlorine molecule, and we know chlorine is a nonmetal. So if I look at a chlorine atom, here's Cl, we know it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Now, it is not stable. In order for it to be stable, it wants a full octet. In other words, it needs to gain another electron. But instead of gaining an electron, what if it shared an electron with another chlorine atom? So here's my other chlorine atom. 1, 2, 3, 4, 5, 6, 7. And what I can see here is this shared pair of electrons between these two chlorine atoms. Now, each chlorine atom has a full octet and it's much more stable. So we define the term molecule as a group of atoms held together by covalent bonds. There are 7 molecules that are identified as diatomics. These are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if you look at the location of these molecules on the periodic table, you'll notice that there's 7 of them. So let's find them. Let's start with nitrogen, which is right here, oxygen, fluorine, chlorine, bromine, and iodine, which is right here. And then finally hydrogen, which just has to be special and over here. You can almost see that it makes a 7, so we call it the diatomic 7. It almost makes a 7 on the periodic table, except of course for the hydrogen, which just has to be special. So in the future, when we talk about chemical reactions and as we get into chemical formulas, if we refer to hydrogen gas or nitrogen gas or oxygen, fluorine, chlorine, bromine, or solid iodine, we're not going to represent them anymore as single atoms. That would be ridiculous because they're very unstable by themselves. Instead, we refer to them in their diatomic form because they are much more stable this way in this format. Now let's shift gears a little bit and talk about coordinate covalent bonding. And here's one of my favorite reference tables. Reference table E are selected polyatomic ions. Many, but not all, of the polyatomic ions contain a special type of covalent bond called a coordinate covalent bond. And that's what we're going to talk about right now. Polyatomic ions generally consist of atoms of more than one element. These are written as dot structures surrounded by a bracket. The overall charge is written as a superscript outside the bracket. The polyatomic ion itself is held together by covalent bonds. They contain at least one lone pair of electrons. This is a pair of electrons on the side of the symbol. a lone pair of electrons is different from a shared pair of electrons. So let's point this out. Here we have HCl. HCl has 3 lone pairs. Lone pair right here, and right here. All of these are referred to as lone pairs because they're pairs of electrons that belong to this chlorine atoms that, you know, are alone. In contrast to a shared pair of electrons, where an electron is being shared between the hydrogen atom of, hydrogen and an electron from chlorine. This is a shared pair because each of these atoms is sharing that pair of electrons. Let's look at a simpler approach of drawing a Lewis dot diagram of the ammonium ion. So we're going to begin by drawing an ammonia molecule, which is NH3, where the hydrogen atoms are covalently bonded to a central nitrogen atom as a shared pair of electrons. So we're going to have a nitrogen, which we know has 5 valence electrons, 1, 2, 3, 4, 5, and that's going to hook up with 3 hydrogen atoms, each hydrogen atom having 1 valence electron, right, just like that. And there we go. And now I can say, all right, this is a shared pair, this is a shared pair, that's a shared pair. Hey, that's great. They're all covalent bonds. But the ammonium ion is NH4 plus 1. So we're missing a hydrogen ion here. We have this hydrogen ion, H plus 1, and that has 1 proton and no electrons. And we know that for hydrogen to be stable, it wants 2 electrons. So that hydrogen ion is going to snuggle up over the top of that lone pair right here. So I'm going to say, hey, let's snuggle up next to this lone pair, and as a result, this ammonium ion is now going to have a plus 1 charge because that plus 1 charge carried over. So the ammonium ion is NH4 plus 1. So in other words, a hydrogen ion lacks electrons as it's composed of a single proton. When the hydrogen ion bonds to the lone pair on the nitrogen in the ammonia molecule, the nitrogen atom contributes both electrons in the lone pair to share with the hydrogen ion. This specifically is a coordinate covalent bond. Let's look at another example. Now let's look at the hydronium ion. So we're going to start by drawing a water molecule where the hydrogen atoms are covalently bonded to a central oxygen atom as a shared pair of electrons. So here's oxygen, 1, 2, 3, 4, 5, 6. Here's my 2 hydrogens. Here's 1. Here's 2. And these are my shared pairs of electrons right here. Shared pairs. Each atom is donating an electron. They've got their full octet. Oxygen's got 8. Hydrogen's got 2. Everybody's happy. But a hydronium ion looks like this. H3O plus 1. So we have a hydrogen ion again, and remember, a hydrogen ion lacks electrons as it's composed as a single proton. When the hydrogen ion bonds to one of the 2 lone pairs on the oxygen in the water molecule, the oxygen atom contributes both electrons in the lone pair to share with the hydrogen ion. So here's my hydrogen ion right here. And let's have it, let's have it go to the top. There it is. It's up on the top. It's now going to form a coordinate covalent bond with the water molecule. I'm going to bring that plus 1 charge with me, just like that. And now the overall charge on this ion is plus 1. Because all we've done is added a proton. We haven't added in any electrons. It's just a proton. And 1 proton is, positive. So again, we have a coordinate covalent bond in this particular polyatomic. The majority of the polyatomic ions on table E contain a coordinate covalent bond. So what is this? A polyatomic ion can be involved in an ionic bond with an ion of an opposite charge. So a sodium ion, Na plus 1, and a sulfate ion, SO4 minus 2, can combine to form sodium sulfate. Now you might say, well, what do you mean by this? What does this look like? Well, let me show you. So I've just drawn a polyatomic ion of sulfate. And you might be saying to yourself, what the heck is going on there? Well, here's what I want you to look at. And don't worry about drawing this. The sulfur in the center has 6 valence electrons. We can see them as the blue X's, okay? 2 on one side, 2 on the other, and 1 by itself on each side. There's our 6. Then we have the oxygens. Oxygen also has 6 valence electrons. And in some situations, as you can see here and here, you can see that there are shared pairs of electrons between the oxygen and the sulfur. All good, not a problem. But for 2 of these shared pairs, which are outlined in light blue, those specifically are coordinate covalent bonds, where a lone pair from the sulfur shares its 2 valence electrons with the oxygen, giving it a full octet. Notice, there's no sharing from oxygens, sharing from sulfur situations here. That's not happening. Instead, both valence electrons are being shared with those 2 oxygens. That's a coordinate covalent bond. Now you might be saying to yourself, but Dr. English, 2 of those oxygens are lacking electrons, so what's up with that? Well, as you can see over here, here's 2 sodium atoms, and they each have 1 valence electron apiece. So let's imagine for a moment that these sodium atoms give up their 1 valence electron and donate it to the oxygen right here. There's donating 1, and this is coming over here, and it's donating the other 1 right here. As a result, it loses its 1 valence electron, and now we have Na plus 1 and Na plus 1. In other words, 2 sodium ions with a plus 1 charge. As a result of this sulfate monstrosity gaining those 2 electrons, now each oxygen has its full octet, whether it has a coordinate covalent bond or a regular old covalent bond. And now this molecule has an overall charge of, you guessed it, minus 2. So now I have SO4 minus 2. And ultimately what you're going to see is that the 2 sodium ions are going to combine with the 1 sulfate ion, SO4 minus 2. And since there's 2 here, we're going to say, well, I need 2 sodiums to cancel out that negative 2 on the SO4, and I'm going to be able to make this formula. Now really, what's the takeaway here? The takeaway is not drawing a sulfate ion. The takeaway is to see how you can have a transfer of electrons. Now I can see here that these are all some type of covalent bonds, whether coordinate covalent or regular covalent. But the bond between the sodium and the sulfate is an ionic bond, and that's key to the future. So file that away for right now, and we'll come back to it. Finally, let's talk about multiple covalent bonds. Let's start with a double covalent bond, where 2 atoms share 2 pairs of shared electrons. So let's look at diatomic oxygen as our example. So I have oxygen, 1, 2, 3, 4, 5, 6. Sort of sad looking X. Here's another oxygen, 1, 2, 3, 4, 5, 6. And I'm going to join these together to form covalent bonds. So here's 1, and here's the other. So this is a Lewis dot diagram of diatomic oxygen. So we could see it's sharing 2 pairs of shared electrons for a total of 4 electrons shared. Now, what you might see in terms of a structural formula of this, which we'll get onto later, but you might see this more commonly as an oxygen double bonded to another oxygen. We'd only see the lone pairs being shown here, and the shared pairs would be represented as lines. Let's look at another example of a triple covalent bond, where 2 atoms share 3 pairs of shared electrons. Let's look at diatomic nitrogen. So we have nitrogen, 1, 2, 3, 4, 5. We have another nitrogen, and I'm putting my lone pairs, because I know nitrogen has 1 lone pair, as far away as my bonding pairs as possible. So 1, 2, 3, 4, 5. And again, I'm going to pair these up. So this is a shared pair, that's a shared pair, and that is a shared pair. So we have 3 pairs of electrons between these 2 nitrogen atoms for a total of 6 electrons shared. What would this look like for a structural diagram? Again, we do a nitrogen, we do a line to represent each of these shared pairs. So there's my triple bond, another nitrogen, one lone pair, and the other lone pair represented. So what did you learn? We did a small introduction to covalent bonding, which we're going to do a lot more of. We went over the definition of a molecule and specifically a diatomic molecule. We did a lot with coordinate covalent bonding, which we'll return to later on in the year. And then finally, we wrapped it up with multiple covalent bonds. Need more help? Feel free to contact me. Have a great day.